Hello everyone, welcome to this brief presentation. Today we're going to delve into the topic of uncertainty quantification, especially applied for a specific study in the computational fluid mechanics domain. So first, uncertainty quantification. Why and which is the question that study and that we want to solve. So we start imagining having some inputs data for a system. With these input, you feed your system and you get some outputs. In computational fluid mechanics, your system is your CFD case and your system is your CFD solver. The uncertainty quantification, in an extremely simplified version, wants to identify which input has the highest influence on the output results. Now we will see a practical example solving the flow around an airflow. For this case, we have a lot of different inputs: velocity, turbulence intensity, angle of attack. These are called aleatoric variables. The uncertainty is coming from the instruments. For example, when measuring the speed, we usually adopt a pitot tube, which has a specific accuracy, but in general, experimental instruments have a specific one. Even your ruler, for example, can have one. Then we have the epistemic variables. They depend on the model that we're using. In specific, for this specific CFD case, we adopt an incompressible model using the k omega SST coupled with the gamma ray theta transitional model. These are numerical inputs which are based usually on empirical correlations, and they are not absolute truth either. For most of the cases, they work just fine. So when solving a classic CFD case, we select a single value for all these variables. We use these inputs to feed our CFD solver, which can be StarCCM, Fluent, or OpenFOAM. And then after the simulation is converged, we get some outputs. In this case, we are monitoring lift and drag coefficient, separation, and reattachment location. However, is our velocity really 10, or can be, for example, be 10.1, or I don't know, 10.3, or some other value? If we measure it in flight or in the wind tunnel multiple times, we will get slightly different values. In the example here, over 1,000 measurements, approximately 50 times we will get 10.0, and more or less 10 times we will get something more or less like 10.4. From one measurement, the red line here, we get one value, but we're not sure is a correct one. We should try different values for our simulation. But while limiting our analysis only to velocity, we have to do this reasoning for all the inputs variables that we need to sample each one from a specific and different distribution, producing each time a new set of inputs, as you can see on the right. So a new set of inputs is generated each time you are sampling from our distribution. So with all this new set of inputs, you have to run our CFD solver. In this case, we will obtain a different value of CL, CD for each set of inputs that we are testing. As you can see in the pictures, each simulation is providing a slightly different value of CL and CD than the other ones. For CL, you see, they are more or less aligned into two lines, while for CD they tend to concentrate on low values. You can see clearly them from the cumulated histogram. Similarly, for the CF curves, the curve of the skin friction on the suction side. From the one of the first simulation, it's possible to obtain separation and reattachment point. Same for the curve coming from the second simulation, and then for the third one, and then also all the others. So with all these outputs, CL, CD, separation, and reattachment, we can plot them together in a graph. I know, it seems scary, this plot. So on the y-axis, for the first 9 vertical lines, are reported the values of the input, while the last 4 are the outputs. Each line has a unique color representing a simulation. These lines are connecting the values of each input values for one specific simulation and the output values. I would like you to focus on the CD output on the right. The lines are colored accordingly to the value of CD that they lead to. So high value of CD lead to yellow lines, while purple, blue to lower level of CD. From this, you see immediately that high levels of CD are due to low S1 and also linked to early separation and delayed reattachment. Stop the video to take your time to study it. The last step is to compute the Sobol indexes. They are a measure of how much an input parameter is impacting a specific output. In general, alpha 1 and S1 are the one with the highest impact for this specific case. And analyzing the previous graph, low A1 and S1 lead to early separation and delayed reattachment, and so to high CD. For this example, we have run more than 500 simulations. But are they enough? We can see it with the cumulative average. So we take the value coming from the first simulation and we plot it. Then we take the second value and we average it with the values of the first one. Then the third, and we average it with the value of the first and the second, and so on and so on. We will see that at one point the average is stable. You can do the same with the standard deviation also, and you will see that also the standard deviation is going to be stable and not to change after a certain number of simulations. So in conclusion, 500s are more than enough, probably also 300.